Hi, my name is Anais Möller, and I am going to tell you about Type 1a supernova from the Dark Energy Survey. I'm currently recording this from Australia. I work at Swinburne University, where I'm an ARC DECRA fellow, and I will also tell you not only about the Dark Energy Survey, but how we can take that analysis that we have developed towards the future for Rubin. Dark Energy Survey main goal, as you can see from the name, is to prove the nature of dark energy. And for that, it uses galaxy cluster, weak lensing, large-scale structure, and Type 1a supernova as cosmological probes. The footprint is on the top right on red. But for the Type 1a supernova survey, we have 5 years of data in the blue and red circles within that footprint. So we basically have a deep drilling field there where we were monitoring for supernova. So you can see that the magnitude limits are close to the one expected from Rubin. To give you an idea of the data quality that we have, here I'm showing an image of NGC 253 from the Dark Energy Survey, and we're not only detecting supernova close by, we're going very faint, and we're finding this galaxy where a supernova is happening on the bottom right. And using this Type 1a supernova, we want to measure the equation of the state of dark energy. So for this, we have the brightness evolution over time of this supernova. So this is what we call a light curve, brightness or flux or magnitude as a function of time in 4 band passes, so photometric filters, GRIZ. And then the other part of the ingredients for making our constraints, and our cosmological constraints, is to get the redshift, either from the supernova or the host. Actually, the host is much better. For this, we get a spectra. We did this here in Australia with the AAT, with a survey called DES. And we get a spectra from the host galaxy and also supernova that were detected live and identified live to trigger follow-up. Now, if we take the 5 years of data of the Dark Energy Survey, that gives us around 30,000 supernova candidates. Now, we expect from simulations to get 2,500 Type 1a supernova that are well sampled for cosmology. Now, if we take only the ones that were classified in real time while we were doing the survey with the spectroscopy, then we have around 400 Type 1a supernova. And this was the traditional way we used to do cosmological analysis with Type 1a supernova. We will classify them using spectroscopy. But this means that we lose a large amount of supernova that we have detected in the survey. So how do we harness more of them? So during many years, we have developed photometric classification algorithms, and I developed in 2020 one called Supernova. It's open source, so everybody can use it. It's based in recurrent neural networks. So the idea is at any point of the light curve, we can get a probability of this light curve being a Type 1a supernova or not. It requires the light curve. But if you give it extra information like host galaxy redshift, the accuracy can go up more than 98%. So we're talking very high purity sample from data that is actually less than having a spectroscopy. We wanted to do this Type 1a sample for cosmology and astrophysics. So that we want high purity and very good measurements. So what we did was take these 30,000 candidates. We took the host galaxy redshifts that we have from spectroscopy, some quality cuts, of course, and then I trained supernova on simulations from the Dark Energy Survey, very realistic ones, that gives us around an accuracy of 98.6, which is really good. We applied these algorithms to the light curves, we obtained probabilities, and then I put a probability cut and selected 1.4 K high quality Type 1a supernova. So this is the largest sample from a single survey of Type 1a supernova at high redshift. So this is a beautiful sample, and you can see the light curves here. For the cosmology analysis, Maria Vincenzi led an analysis to actually make those cuts even stricter, and you can read it in her paper from this year. The cosmology results are in the Dark Energy Survey collaboration paper from this year. and our data release will be soon out, which is led by Bruno Sanchez. So stay tuned for that one because we have amazing data for this. Now, what's the beauty of photometric classification is that we really can probe higher redshifts and getting better statistics. So here I'm showing in red the spectroscopically classified type 1a supernova, and in yellow you can see the photometrically selected type 1a supernova. And you can see that the power of this supernova is quite high. We can also check if we understand the evolution of color and stretch, which are properties of the light curves as a function of redshift. Here you're seeing in black the data and in gray the simulations, and you can see that it traces pretty well. And this is very important for us because we need to understand those populations evolutions. And we took this sample and did a cosmology analysis. So here is the Hubble diagram from the Dark Energy Survey collaboration that we published in January this year. I'm sure that Tamara Davis will talk a lot about this diagram and how we did the constraints in cosmology. But to give you a little bit of an overview, we have the distance modulus against redshift, and in the top you see in blue all the supernova that we had for the Dark Energy Survey. And we did things a little bit different. Instead of making a cut and saying this supernova goes into a sample or not, we basically did weight the supernova for the analysis using the probability of classification. And you can see in the color map to the right, the probability of being a type 1a from supernova, and that's what we use for the cosmology analysis. Now, on the bottom plot, we're seeing the residuals of a flat WCDM cosmology, and you can see a comparison in purple and in green between flat lambda CDM and flat W0 WA CDM. Here we're talking about a equation of state that is varying with cosmic time. We have tantalizing evidence that this may be the case, but we don't have still the power to say this. So Rubin era will be very, very exciting to see whether it's a flat lambda CDM or we're talking about equation of state that is evolving with cosmic time. Now, of course, the cosmology is in the core of all of us, but standardization is one of the challenges that we have. We standardize type 1a supernova using light curve properties like color and stretch, but also host galaxy properties like mass and other selection biases, etc. So a lot of our effort is also in the astrophysics. What are the properties of this type 1a supernova? Rates and delay times, local environments, galaxy-driven luminosity variations, the host galaxy dust, which is a very hot topic right now. So this photometrically selected sample really gives us the power to take this analysis a step further because we have a lot of statistics that can help us constrain things at higher redshift. Of course, there's a lot of work by the DES Supernova Working Group team. I'm just highlighting a couple of things, but there's much more to come because this year we're putting out all our results on the Dark Energy Survey Supernova team. Now, the question here is, okay, I have 1,400 type 1a supernova. We were supposed to detect 2,500 well-sample type 1a supernova. So clearly, we're missing some of them. And what are we missing? Probably hostless supernova, probably in faint galaxies because it's harder to get a spectroscopic redshift for them. So what I did was I took the same 30,000 type 1a supernova. I filter AGNs. I asked for a sampling in the light curve to like not 2 points, but much like 1 point before maximum, a couple of points in the decay part. And I apply Supernova, which I retrain now only using light curves, no host galaxy redshift whatsoever. So just using fluxes and errors and time, we can get a classifier that can be up to 97% accuracy, which is pretty high for having less information. And then I selected 3,000 type 1a supernova. Now you can see that in the two right columns, These are the spectroscopic and photometric type 1a supernova from the other samples. We still maintain most of them, which is pretty promising. But to interpret the results and understand a little bit the sample, we need redshifts. So if we don't take them from the host galaxy using a spectroscopy, what can we do? So I use an algorithm that actually estimates the redshift from the light curve of the supernova. So it fits simultaneously redshift, color, stretch, etc. from the SALT2 parameters. And here I'm showing you a plot of the estimated parameters against the true for some simulations to check the biases that we're introducing. And you can see it's actually quite good. There is some correlations in the redshift and some dispersion in color, but else is pretty decent. So I took that new redshift that we call SM Photo C, color and stretch, and did some quality cuts, and I obtained 2,400 high quality type 1a supernova. So this is pretty good. This is quite close to the 2,500 that we expected. Of course, there are other options to do this redshift using like photo-Cs from host galaxies, and there is an analysis coming out soon about this. But for the time being, we are just taking information from the light curve here, okay? So the first thing is to check if our color and stretch evolution over redshift continues to track what the simulations tell us. So in light gray is the simulations using the real redshift, and in red is the simulation if we use that redshift estimating from the light curves, and you can see that we can account for those changes that we see in the data that are off, which is pretty encouraging, which tell us we can use this sample and this way of estimating redshift for other analysis. Now I'm gonna move now to comparing 3 type 1a supernovas samples from the same survey to show you the power of them, okay? The first thing is, well, here I'm showing the brightness in peak in I for the type 1a supernova on the left, and the host galaxy magnitude, so how faint it is, on the right. And you can see that for the SM Photo C sample, which is the green one, compared to the one that we use in cosmology in orange, compared to the spectroscopically classified in blue, we are really reaching fainter host and fainter supernova as well. So this is not necessarily correlate with the redshift. It can be part of high redshift, but it can also mean that at closer redshifts, we're targeting things that were not targeted before. And you can see it here because we have, of course, more supernova at higher redshift, but you can also see that around 0.6, we're really getting much more supernova. Now, in color and stretch, you can see like the skewness of the distributions is a little bit different. So this is interesting because we're understanding the population of type 1a supernova. And one of the big hot topics right now is the correlations between the light curve parameters like stretch, which is marked here as X1, as a function of the mass of the host galaxy. So in gray, I'm showing all the supernova from this sample, this new sample. In blue is the spectroscopically type 1a. In orange is the one used for cosmology. And in green, the new one, okay? And you can see that if you see a difference between the host stellar mass to the left of the 10, so less than 10 or higher than 10, the differences between them, each sample is a little bit different. You can see a bigger offset between the blue and the orange samples than in the green one. So you can ask yourself, is this a selection bias? Is this something introduced by this redshift that I'm computing at the same time like X1? So I took the same sample and just restricted to the ones that had spectroscopic redshifts. And we still see a smaller offset between low mass and high mass, but it's something that we're still investigating. And I think this is going to be very interesting for the years to come to understand this correlation between supernova and their host galaxies. Now, I'm going to finish up talking about prospectives for Rubin. How do we take photometric classification to the next level? How do we use it for Rubin? So in DES, we have 30,000 candidates that we wanted to do follow-up for host galaxy spectra. So the old method was that we took some sampling of the light curve, we fed some templates and selected the ones that we wanted to target. Now, the horizontal line is the number of targets that we have. So we have more candidates that time in the telescope, of course. And in orange, I'm showing the type 1a supernova that were in that sample, okay? Now, can we do something better with machine learning? If you apply supernova without any redshift information, you can reduce the number of candidates while maintaining the number of type 1a supernova. And I think this is pretty exciting because we're actually optimizing our resources. This is completely reproducible. It's just a probability cut, and you can maintain your type 1a supernova, use better your telescope time, do a lot of science with that. The other question is, can you find this very early, this type 1a supernova? So you want to target it before maximum light. And one of the things for Rubin is that if you only take the first signal to noise bigger than 5 detection, shown here in yellow in the light curve, as your starting point of your light curve, you're going to lose a lot of them. You need to use a criteria like we use in the dark energy survey, where you take a couple of detections within a time window to actually get around that early rise of the light curve. Now, if we use a DES-like trigger, we maintain most of the type 1a supernova and keep the number of potential candidates actually quite low, which is very good because we can optimize our early classification. In the last minute, I'm going to show you a little bit how we're preparing for Rubin with FINC and CTF data. Supernova is part of FINC, and we have a filter that uses 2 machine learning classifiers to detect early type 1a supernova candidates. You can see that we have reported over 1,000 early type 1a supernova candidates to TNS, and they have been followed up. We're still improving these and making advancement, also using a recommendation system with active learning, which soon will be published. And we're also preparing with simulations. So using Elastic version 1, we're trying to find supernova-like light curves and disentangle them from other transients. So in summary, I think dark energy survey is a beautiful sample, the largest high redshift sample from a single survey used for cosmology. We have the tightest constraints of dark energy from supernova to date. And in the Rubin data, we really want to use photometric classification to get most of the type 1a supernova to optimize follow-up either for host on or early type 1a supernova. And of course, I'm looking forward to your questions. I'll be connected, but my email is down here. Thank you.